Paula Burkhardt-Guim, and she's going to speak about C0, ADM mass, and distortion under Ricci-DeTurck flow. Please.
Okay. Well, yeah, thank you very much for the introduction and for the invitation. And also, I would like to thank the organizers for letting me participate virtually. Yeah, I would have loved to be there in person, but somehow this semester is like kind of a mess. So anyway, let me first give you a little bit of context for kind of how I came to this problem. So my background is in Ricci flow. And so the context for what I'm going to tell you about today is that, somewhat recently, I think there has been a lot of interest in studying problems involving, spaces with lower scalar curvature bounds in some kind of non-smooth setting. So for instance, maybe you have a sequence of Riemannian metrics that have scalar curvature bounded below, and they're converging in some kind of non-smooth sense. And then relatedly, there's also been a lot of work on defining sort of synthetic notions of lower scalar curvature bounds for various classes of non-smooth metrics. Okay, so let me just tell you an example of a result kind of in this area. So this is due to Gromov from 2014. And so this theorem says the following: let M be a smooth manifold and kappa from M to R a continuous function. And suppose we're in the following situation. So suppose we have a sequence of Riemannian metrics GI. Okay, so these are just C2 Riemannian metrics. And suppose they're converging uniformly to some limiting metric. Okay, so somehow, even though we have only C0 convergence here, let's assume that somehow we know that the limit is a C2 Riemannian metric. And let's also suppose that each metric in my sequence, so each GI, has scalar curvature at x bounded below by kappa of x, right? So here kappa is a function, the scalar curvature is also a function, and the scalar curvature satisfies this pointwise lower scalar curvature bound. Okay, so yes, as I said here, these are C2 metrics, and the limit is somehow also C2. And then the conclusion of this theorem is that then the limiting metric satisfies the same pointwise lower scalar curvature bound. Okay, so in other words, this is saying that pointwise lower scalar curvature bounds are preserved under uniform convergence. So, this is a little bit surprising. Like here, we only have uniform convergence, and scalar curvature, involves second derivatives of the metric. So you wouldn't really expect to be able to say much about the scalar curvature of the limit. And yet these lower scalar curvature bounds, the pointwise lower scalar curvature bounds, are preserved. Okay, and so, this is an example of the sort of work in the area that I was talking about, where, we have some spaces with scalar curvature bounded below these metrics GI, and then the non-smooth thing that is happening here is that we have C0 convergence. Okay, and so the way that Gromov proved this is that he recognized that, even though this property of having a lower scalar curvature bound is a statement about the scalar curvature, which involves second derivatives of the metric, that actually somehow you can kind of reformulate this property solely in terms of C0 phenomena. And so then if having this lower scalar curvature bound only depends on C0 phenomena, then somehow it's not surprising that it would be preserved under uniform convergence. Okay, so this is kind of how Gromov approached the problem. And then somewhat more recently, I think there has been some interest in using Ricci flow to study these types of problems. Okay, so for example, in 2016, Bandler came up with an alternative proof of this theorem of Gromov using the Ricci flow. Okay, and so I will talk a little bit more about, how this proof of Bandler works in a moment, but let me just first remind you what are the Ricci and Ricci flow, what the Ricci flow is. And then I will also talk about the Ricci-DeTurck flow. So the Ricci flow is, an evolution equation for Riemannian metrics on a manifold. It's this evolution equation. Okay, so for me, I actually don't work with Ricci flow that much. And so my Ricci flows always have these tildes on them. All right, and so the Ricci flow equation is that the time derivative of the family of metrics at time t is equal to -2 times the Ricci curvature of the time slice at time t. And of course, you can prescribe some initial data. All right, and so, today, actually, rather than working with Ricci flow, which is, a nice flow, I'm going to work with a different but very closely related flow, which is called the Ricci-DeTurck flow. And so here's the Ricci-DeTurck flow. Okay, so, what is the point of the Ricci-DeTurck flow? Well, the idea is that, even in the case of smooth initial data, if you're trying to find a solution to the Ricci flow equation, one thing that you have to contend with is that this Ricci flow equation is not a strongly parabolic equation. Okay, and so one way that you can deal with this is an idea of DeTurck, is to first solve a different equation, which is strongly parabolic. And then hopefully after solving that equation, you can pull that solution back by a family of diffeomorphisms to get a Ricci flow. Okay, so the related equation you solve, which is strongly parabolic, is the Ricci-DeTurck flow. And somehow, it's actually, okay, so this is some vector field, and it's not so hard to check that if you have a solution to the Ricci-DeTurck flow, then you can easily turn it into a solution to the Ricci flow by pulling back by the family of diffeomorphisms generated by this vector field X. So the way that I've written down the Ricci-DeTurck flow here, it doesn't look like it would be much easier to deal with than the Ricci flow, but it turns out that actually, this vector field is chosen in such a way that this is analytically a bit better behaved. Okay, and so so this vector field is some time-dependent vector field, and it also depends on a choice of smooth background metric. For me, we're just going to work on Rn, and so the background metric that I'll choose is always Euclidean space. Okay, so I'll just specify that now. Okay, and then of course, as before, we can prescribe some initial data. Okay, so here are the Ricci and Ricci-DeTurck flows. Why am I talking about these? Well, we were talking about problems involving spaces with scalar curvature bounded below, and using Ricci flow and Ricci-DeTurck flow to solve problems related to such spaces. And so the reason that you might guess that Ricci and Ricci-DeTurck flow are related to spaces with lower scalar curvature bounds is that uniform lower scalar curvature bounds are preserved under these flows. So what I mean is that if your initial data G naught has scalar curvature bounded below by some constant kappa naught, okay, so here this is a constant, not a function, then for all positive times for which the flow is defined, the scalar curvature of every time slice of the flow will also be bounded below by kappa naught. Okay, so that is one reason that you might guess that Ricci and Ricci-DeTurck flow are kind of related to problems involving lower scalar curvature bounds. The other thing that is kind of nice about Ricci and Ricci-DeTurck flow in particular is that they kind of smooth things out, right? So we were talking about problems involving scalar curvature bounded below, but we have some sort of non-smooth thing happening. And so the idea is that, well, if you run the Ricci-DeTurck flow, say, starting from, one of these non-smooth spaces, or spaces where you have some kind of non-smooth convergence, then the Ricci-DeTurck flow will smooth things out nicely. Okay, and so let me just now tell you a lemma that kind of illustrates the fact that Ricci-DeTurck flow provides a smoothing of a metric. Okay, so this lemma is due to Courant-Lemma, and it says the following. There exists some constant bar epsilon less than 1 and some positive constant such that the following is true. If G naught is any C0 Riemannian metric on Rn, such that G naught minus delta is smaller than bar epsilon in the C0 sense. Okay, so this is the Euclidean background. Then there exists a smooth Ricci-DeTurck flow GT defined for all positive time such that the following are true. So first of all, this flow converges locally uniformly to the initial data as t goes to 0. Second of all, the flow stays close to this Euclidean background in the sense of this X norm. Okay, so here our initial data, started out as small. So the initial metrics started out being close to the Euclidean metric. And this is saying the flow will continue to stay close to the Euclidean metric. And actually, it's not just going to stay close in C0, but we get a little bit better. So we have this L infinity part. But also, it's staying close in the sense of this X norm. So we have some control. Oops, I'm missing a bar here. We have some control on these quantities as well. Okay, and so actually this kind of the specific form of this norm will become a little bit important for us later. And then finally, also the flow gives you some control on the derivatives. Okay, so the kth derivative at time t is going to be bounded by the initial distance of the metric to Euclidean space divided by t to the k/2. Okay, so what is this saying? This is saying that suppose you have, a small C0 perturbation of Euclidean space, well, then you can find a smooth Ricci-DeTurck flow that sort of corresponds to that piece of initial data that is, very well behaved for positive times. Okay, so technically in their paper, they did not state this particular fact, but it is true. And then also I should just say, so they also looked at initial data that was only L infinity by Lipschitz to Euclidean space, but for the purposes of this talk, we will only do C0. Okay. And so now I'm going to try to convince you that a result like this is quite useful if you're studying spaces with scalar curvature bounded below. And so let me just show you an argument that you could do using this lemma. Sorry, actually, maybe I will just say here, for the purposes of today, we only care about flows on Euclidean space, but there are sort of similar results for flows on manifolds. And so if you want to look at like Ricci-DeTurck flow for C0 metrics on manifolds, there's some work of Miles Simon. Sorry. From 2002, which has slightly different estimates than what you see here. And then I also looked into this a little using similar norms to those of Koch and Lamb. But okay, anyway, for us, we will just think about Euclidean space. And so let me try to use this lemma to do kind of a nice argument involving spaces with scalar curvature bounded below. So let's suppose that we just want to prove Gromov's theorem. The theorem, again, was that pointwise lower scalar curvature bounds are preserved under uniform convergence. Let's suppose we want to prove that in the case where we know all the metrics in our sequence are small perturbations of Euclidean space, and we just want to prove it where the lower bound is a constant rather than a function. Okay, so if we wanted to prove something like that, here we have our sequence of Riemannian metrics. They're converging to some limiting metric. And then what I could do is, using this lemma of Koch and Lamb, I could run the flow, the Ricci-DeTurck flow, starting from each metric in my sequence. And I could run the flow starting from this limiting metric. And then somehow we saw by these derivative estimates due to Koch and Lamb that the Ricci-DeTurck flow is going to turn the uniform convergence of the initial data into locally smooth convergence of the flow for positive times. Okay, so we'll have something like this. This is for t greater than 0. Okay. And so now, we're assuming that these satisfy some lower scalar curvature bound, some uniform lower scalar curvature bound. We want to show that the limit satisfies the same uniform lower scalar curvature bound. So we could argue as follows. Well, each GI satisfies some uniform lower scalar curvature bound. The uniform lower scalar curvature bounds are preserved under Ricci-DeTurck flow. So for all positive times, the GI of t are going to satisfy that same uniform lower scalar curvature bound. And then at positive times, we have locally smooth convergence. So the limiting flow is also going to satisfy that uniform lower scalar curvature bound. And then if we just let t go to 0, we'll find that the limit satisfies the same uniform lower scalar curvature bound. Okay, so this is kind of like a baby version of Bandler's proof, just in the case where the lower bound is a constant and all of these metrics are like little perturbations of Euclidean space. But hopefully this illustrates kind of why the Ricci-DeTurck flow is a kind of nice tool in this setting, because basically, first of all, it preserves lower scalar curvature bounds. So you can still study the setting of lower scalar curvature bounds after you evolve.
May I ask a question? So I'm a bit confused about, so, I mean, why in the, in the final step, the scalar curvature bound is preserved? Maybe it's a silly question,
coming
but
down.
I'm just, yeah.
Yeah, so it turns out that if this is C2, then you'll have C2 convergence going down, but yeah.
Okay, that's the point. So the convergence, okay, thanks, okay.
No problem. Anyway, so let's see. So, hopefully this kind of convinces you that Ricci-DeTurck flow can be useful for studying these problems with scalar curvature bounded below, because, it will preserve your lower scalar curvature bounds, but also it smooths things out. So it kind of improves things. Okay. So by the way, this argument, suggests a very kind of natural synthetic notion of a lower scalar curvature bound for metrics that are only C0. Namely, we could say that a C0 Riemannian metric has non-negative scalar curvature, let's say in the sense of Ricci flow, if there exists a Ricci-DeTurck flow for it, such that for all positive times, the Ricci-DeTurck flow satisfies the lower scalar curvature bound. Okay, and so, what I showed a couple years ago now is that this definition can be localized. So there's kind of a meaningful way of using Ricci-DeTurck flow to talk about what it means, for a C0 Riemannian metric to have a lower scalar curvature bound at a point or on an open set. Okay, and so this localization is like maybe a little bit in the background of what I'll talk about today, but I think, maybe saying all the details about this will not be very instructive. So, but basically, this is kind of a nice notion of non-negative scalar curvature. You can declare that a C0 metric has non-negative scalar curvature if you can find a Ricci-DeTurck flow, which for positive times has non-negative scalar curvature. And there's kind of a nice way to localize this. Okay. Before I continue, I just wanted to mention a couple of names of people who are doing kind of related things. So there are some very compelling notions, sort of distributional notions of non-negative scalar curvature for metrics that live in some Sobolev spaces. Yes?
So in the previous theorem, you had arbitrary constant lower bound. Now you passed to zero local bound. Is that because the other constants don't localize, or?
No, they both do. I just, for some, I don't know. Yeah, I could also have a constant here.
Thanks.
Mm-hmm. All right, and so, there have been some compelling notions of, non-negative scalar curvature in some distributional sense for metrics in various Sobolev spaces. And somewhat recently, like in the past year, people have been studying Ricci and Ricci-DeTurck flows coming out of these spaces. So I think, this has a slightly different flavor because you use distributional derivatives, but I think this is some very interesting work. Okay. So anyway, to summarize, the idea is that you want to study some space that has scalar curvature bounded below. There's something non-smooth happening. And so what you should do is you should then run the Ricci-DeTurck flow starting from those non-smooth, whatever situation you were originally in, and it will somehow smooth things out. Okay. All right, so all of this context leads us to ask, well, can you only do this for lower scalar curvature bounds? Or could you kind of play a similar game with other metric quantities that are somehow associated with the scalar curvature? And so, of course, okay, here we go. So yes, so can other quantities that are associated with lower scalar curvature bounds be understood solely in terms of C0 data of the metric? And then if so, how do these quantities behave under evolution of the metric by Ricci or Ricci-DeTurck flow, and can we learn anything from studying them in this way? Okay, so of course, one such quantity is the ADM mass, which, I'm sorry to repeat it. I think everyone is very familiar with it. But okay, here it is. So if we have some smooth Riemannian metric now and a coordinate chart phi from M minus a compact set to Rn minus ball, then the ADM mass is given by the following limit. Okay, so here we have a normalization constant. Here we are integrating over a coordinate sphere of radius r, and we're integrating this, this coordinate expression involving derivatives of the metric. Okay, and so, of course, the reason I say that this is a metric quantity that is associated to lower scalar curvature bounds is because of the Riemannian positive mass theorem. Oh, sorry. Okay, I'm getting ahead of myself. So, of course, if I just write down this expression, it's maybe a priori not so clear whether this limit at infinity should exist. And if so, whether it depends on the choice of coordinate chart. But thanks to Bartnik, and crucial in the asymptotically Minkowski space, we know that under certain conditions, this limit will indeed exist and it will be independent of choice of coordinate chart. So, Bartnik says that if in some coordinate chart, we have the following, so the metric decays to Euclidean space like x to the minus tau for tau, at this decay rate. And then also the first and second derivatives decay to 0 at this rate. And also if we know the scalar curvature is in L1, then this limit does in fact exist and it is independent of choice of coordinate chart satisfying these items. Okay. And so, as I said, the reason I am saying that the ADM mass is a metric quantity that is associated with lower scalar curvature bounds is of course because of the Riemannian positive mass theorem. Okay, and so again, I think people are very familiar with this, but this just says that suppose if we're in the setting of the result of Bartnik, well then if the scalar curvature is non-negative, the ADM mass is also non-negative with equality if and only if G is flat. Okay, and so. Oh, and maybe I should just say, so, here I've stated everything as if you have a manifold with just one asymptotically flat end. Of course, the positive mass theorem is also true if you have a manifold with multiple ends, and the things I will state today also work if you have multiple ends. But anyway, okay, more on that later. So, you know, of course, I am interested in the C0 setting. That's kind of where I'm coming from. So let me just highlight everything in this statement that is not C0. So first of all, I'm talking about decay of the derivatives of the metric. This is not C0. If you just had a C0 metric, it wouldn't have derivatives. And then also, you know, there isn't really a well-defined notion of scalar curvature. So I don't know how to talk about the scalar curvature being in L1. Now, you know, rather than having non-negative scalar curvature, if my metric were only C0, I could replace this condition with a condition that we had non-negative scalar curvature in the sense of Ricci flow. So let's say in the sense of Ricci flow. Okay, and then somehow we need to make sense of the ADM mass and, you know, saying that the ADM mass is not negative. Okay, so, you know, I don't want anyone to feel misled. I am not asserting that this theorem is true. I'm not saying that I have proven a C0 version of the positive mass theorem. I am just saying that, you know, I think it would be interesting to prove a statement of this sort. And so this is the setting in which I am going to sort of investigate how to make sense of the ADM mass. And, you know, I guess because of my background, I think it's sort of interesting if we can figure out, well, you know, do we have the notion of ADM mass that has sort of controlled distortion under Ricci-DeTurck flow, and what does, you know, how does that work? Okay, and so let's see, what did I want to say? Okay, so I'm going to say if you have a metric that only satisfies this this property in some coordinate chart, that it's C0 asymptotically flat. So the coordinate chart is still smooth, like the manifold still has a smooth structure, but the decay is only C0. Okay. And so, you know, as I've been kind of describing this problem, I think many of you probably think, well, yes, of course, we have some very nice C0 notions of ADM mass. For instance, we have Huskyn's isoparametric mass, we have Jarghi's isocapacitary mass. These both make sense for C0 metrics, and that is certainly true. Today, I'm going to take maybe a slightly different approach that I think is also natural. And I guess the reason I kind of took this approach in the first place was because it was like somehow very easy to read off what would happen then to the sort of corresponding local mass under Ricci-DeTurck flow. Okay, so now I will tell you the details of that. Okay, and so, you know, towards making sense of the ADM mass for metrics that only have C0 data, let me maybe just make the following observation. Okay, so here in the definition of ADM mass, I'm integrating over a single coordinate sphere. Okay, but I could just as easily integrate over a family of coordinate spheres weighted by a test function. Okay, I think this is pretty natural. And so here I have done just that. So here I'm integrating over a family of radii from 0.9r to 1.1r. Weighted by this test function phi. And so here I'm, you know, integrating this coordinate expression over the corresponding coordinate sphere. Okay, so this is, you know, perfectly natural. And then if I wanted to let r go to infinity, of course, I could somehow do a change of variables. Okay, so here now I've done a change of variables. So here, here the r has moved into the radius of this coordinate sphere. And, you know, the point is just that if you're in a situation where you already know that the ADM mass exists, then this expression is going to converge to the ADM mass. Okay. Oh, I dropped a normalization constant, but okay. After putting back this constant, this expression is going to converge to the ADM mass. Okay, well, why am I doing this? Well, you know, here I'm integrating over a family of radii and then a single sphere, but I could just as easily integrate over an annulus. All right, and so then if I integrated over an annulus, this would look like the integral over an annulus of some smooth test function multiplied by something that has some derivatives. And then if I wanted to get rid of the derivatives, I could do sort of the classic thing of integrating by parts to put all the derivatives onto the test function. Okay. And so if I were to carry that out, I would get the following expression. Okay, so here, as I said, I'm integrating over an annulus. And then now, you know, as a result of putting the derivatives onto the test function, I get these terms involving the test function and the derivative of the test function. Okay, and then here I have this trace term. This is the metric in coordinates. And here I have this sort of radial term. Okay. And then, of course, since I integrated by parts, I get some boundary terms. For me, the boundary terms are always going to be small, if not zero, and so I'm not going to write them. Okay, so anyway, this is, a rather complicated expression, but the point is that somehow this only involves, C0 data of the metric. There are no derivatives here. Okay. Okay, and so, by the argument that I just showed you on the previous slide, I know that if I have a metric for which I already know the ADM mass exists, if I let R go to infinity, then this thing is going to converge to the ADM mass. Okay, but if I have a metric that's only C0, has only C0 decay on the derivatives, like just because I can write this thing down doesn't mean that it's going to converge to anything at infinity, right? And even if it does, maybe it will depend on this choice of test function, maybe it'll depend on this choice of coordinate chart. Okay, so this is what I want to know now. So if I have only a C0 metric that has decay in C0, does the limit as R go to infinity of this quantity, I'll call it like the C0 local mass, does this limit necessarily exist? And then if so, does it depend on the choice of this test function and the choice of this sort of C0 asymptotically flat coordinate chart, right? So obviously I want the answer to this first question to be no, or sorry, to be yes. And then I want the answer to these second two questions to be no. Okay. And so now I will tell you a theorem that answers these questions. And it turns out to have like really good answers to these questions. Here I have a fixed test function, but actually I'm going to need to allow the test function to vary a little bit with R. Okay, and so I'll say a little bit more about how that works later. All right, so here is the theorem. Let G be a C0 metric on a smooth manifold M, and capital Phi from M minus compact set to Rn minus the ball to be some coordinate chart for M, such that in this coordinate chart, the C0 metric decays to Euclidean space like x to the minus tau, where tau is bigger than n minus 2 over 2. Okay. Now let Phi be some non-negative smooth cutoff function with support compactly contained in 0.9, 1.1, and Phi should obviously not be identically 0. Okay. Then there exists a smooth family of functions, phi r. Okay, so these, r is the radius, it's going to vary. That somehow corresponds to phi, such that the following two things are true. So first of all, if I'm in the sort of classical setting and I know the ADM mass exists, then the limit as R goes to infinity of the C0 local mass computed with respect to these this family of test functions, phi r, this will converge to the ADM mass. Okay, no surprises there. This is basically what I told you earlier, except now we're letting phi vary. But maybe the more interesting thing is that if the scalar curvature of G, so now G is just C0 and has C0 decay. And so if the scalar curvature of G is non-negative in the sense of Ricci flow on M minus the compact set, then the limit as R goes to infinity of this C0 local mass also exists. And it's either finite or positive infinity, and it's going to be independent of choice of C0 asymptotically flat coordinate chart and test function phi. Okay, so in other words, yes, a limit always exists, even if you only have C0 data, and no, it does not depend on the choice of C0 asymptotically flat coordinate chart or test function. And there's also some finiteness condition that you can talk about for this mass that is sort of analogous to having scalar curvature in L1, where you instead require basically that the scalar curvature of like the certain time slices of the Ricci-DeTurck flow are in L1, but yeah, I didn't fit it on the slide, so maybe I won't talk about it.
Sorry, when you talk about these Ricci and flows and Ricci-DeTurck flows, at the boundary of K, do you need to say what's happening at the boundary?
Oh no, I mean, okay, so this kind of has to do with this fact that we can kind of, how do I want to say this? So, sorry, also there's an ambulance. That we have this kind of localized definition, so we can talk about what it means for a C0 metric to have non-negative scalar curvature in the sense of Ricci flow at a particular point. So all I'm saying is that that kind of localized definition holds everywhere on here.
Thanks.
Okay. And so, how do you prove this theorem? Well, maybe you have guessed, like this follows from a monotonicity result. And so we can prove some kind of monotonicity result that says that, the sort of C0 local mass at a large scale is always going to be bigger than the C0 local mass at a smaller scale up to some small error. And this is somehow due to this lower scalar curvature bound, this generalized lower scalar curvature bound. Okay. And so, yeah, let me maybe make this a little bit more precise. Okay, so here is the monotonicity statement. Let M be a smooth manifold and G a continuous metric on M. And suppose now we have two C0 asymptotically flat coordinate charts. So I call them capital Phi1 and capital Phi2. Okay, and the decay rates for both are strictly greater than n-2/2. Okay, and so then the conclusion is that there exists some scale bar R such that if G has non-negative scalar curvature in the sense of Ricci flow, basically on the domains of both of these coordinate charts, and you have two smooth cutoff functions with support compactly contained in 0.9, 1.1, then for all R larger than this scale bar R, we have the following comparison. So the C0 local mass with respect to capital Phi I and lowercase capital Phi1 and lowercase Phi1 at scale 200 R is bigger than the C0 local mass with respect to capital Phi2 and little Phi2 at scale R up to this error. So here omega is some positive exponent that depends on tau1 and tau2, and this is going to go to 0. This whole term goes to 0 as R goes to infinity. Okay. Okay, and so how do you prove this? Well, I'm sure everyone here is very familiar, like there's sort of a similar version of this monotonicity statement due to Bartnik if you have a smooth metric with non-negative scalar curvature. Okay, and so somehow what we would like to do is we would like to carry out this calculation of Bartnik. And so what we will do is we'll run the Ricci-DeTurck flow, then we'll have non-negative scalar curvature ostensibly for positive times. And then we'll carry out this calculation of Bartnik at positive time slices of the Ricci-DeTurck flow. Okay, and so then we should get a result that looks like this for positive time slices of the Ricci-DeTurck flow. But of course, that's not what I wanted, right? Because I wanted a statement about the initial data. I don't want just a monotonicity statement for positive time slices of the Ricci-DeTurck flow. And so somehow I need some way of, relating that monotonicity statement that I got for the positive time slices back to the initial data. Okay, and so I need some, estimate on how these local masses are going to distort under Ricci-DeTurck flow. Okay, and so here is the lemma that explains kind of the distortion of the C0 local mass under the Ricci-DeTurck flow. And this is also where we see the fact that we need to let the test function vary with R. Okay, and so maybe I will read it first and then I'll kind of talk about it. So let R greater than 0 be large. Sorry, this is a little imprecise. And eta greater than 0 be small. And let phi greater than 0 be some smooth cutoff function that is with support compactly contained in 0.9, 1.1. And then for t between 0 and r to the minus eta, I'm going to let phi sub r to the minus eta of lt be this sort of evolving cutoff function. And it's going to evolve basically by a backwards heat equation. It's actually going to evolve by this backwards equation. Okay, and so since I have a backwards evolution equation, I need to prescribe some final data. Okay, and so I'm going to prescribe the final data that at time r to the minus eta, this evolving function, oh, sorry, I lost my subscripts, but okay, you know what I mean. This evolving function at the final time is equal to my cutoff function. Okay, so, what is this evolution? Basically, if you have a spherically symmetric solution to the backwards heat equation, this is going to be the evolution of its radial derivative. Okay, and let's also just suppose now that this evolving function is small on the boundary of this annulus. Okay, so you can always achieve this. Oh, sorry, I should. Oh, okay, never mind. So then for all decay rates, tau greater than n-2/2, eta greater than 0, and c0 greater than 0, there exists some scale bar r such that for all r greater than bar r, the following is true. Suppose we have a continuous Riemannian metric on Rn that is close to Euclidean space. Okay, how close is it? So it's close in C0, like C0 to the R minus tau. Okay, so here R is fixed. And let's also suppose that we have some smooth Ricci-DeTurck flow for G0, which satisfies the conclusion of this result of Koch and Lamb. So in other words, here we have a smooth Ricci-DeTurck flow that converges uniformly to the initial data as t goes to 0. This Ricci-DeTurck flow is going to stay close to Euclidean space in the sense of this X norm of Cohen-Lamb. And also this Ricci-DeTurck flow has some control on the derivatives. Okay, so you can always find such a thing provided that R is small. And you can also always find such a sort of evolving cutoff function. And then the conclusion is that, well, if I, couple my C0 local mass with this evolving cutoff function, sorry, I think these absolute values should be outside. Okay. And then I look at the distortion of this local mass. Well, then this is going to have bounded distortion. And I can integrate the distortion up to time r squared minus eta, or r to the 2 minus eta. Okay. So in other words, I want to know, well, if I have some nice monotonicity result for my C0 local mass at a positive time, how can I turn that into a nice monotonicity result for the initial data? And this is saying, well, if you couple this local mass with the correct evolving test function, then the distortion is going to be nicely controlled. Okay. Let's see, was there anything else I wanted to say? Okay, so let's see if I wrote it. So in this in the previous statements, I had these varying test functions, a varying family of test functions. And so you can see from this statement that, at scale R, I want my test function to be this evolving test function, and I want to take the time 0 slice of it. Okay, and the reason is just because then this function, when I evolve it, kind of behaves nicely with this distortion under Ricci-DeTurck flow. Okay. I just wanted to note, okay, again, so I mentioned this, but maybe I will just emphasize it. So here R is some fixed thing. And so actually, when we apply this lemma in practice, what we're going to do is we're going to, restrict the Riemannian metric that we're interested in to a particular annulus of scale R. And then actually we just kind of glue it into Euclidean space and run the Ricci-DeTurck flow from that. And this is, I think it's actually quite surprising, like somehow this is good enough. You actually don't need to have a global Ricci-DeTurck flow in order to do this argument, though you will have a global Ricci-DeTurck flow, but actually somehow the entire argument can just be done kind of at the level of like metrics on annuli, which I think that's kind of interesting. Okay, so maybe let me tell you some kind of natural questions that arise from these results. So first of all, of course, I want to know, well, if I have a C0 metric that is C0 asymptotically flat, and it has non-negative scalar curvature in the sense of Ricci flow, do we necessarily have that the limit of the C0 local mass is non-negative, right? So, somehow what I'm trying to assert is that the limit of this C0 local mass is kind of a reasonable analog of the classical ADM mass, because it agrees with the classical ADM mass whenever it exists, but it's also well defined for, C0 metrics that are C0 asymptotically flat, at least if they have non-negative scalar curvature in the sense of Ricci flow. And so this statement would be saying, well, there's sort of a C0 version of the positive mass theorem if you have non-negative scalar curvature in the sense of Ricci flow. So yeah, I would like to know if this is true. And then of course, I would like to know whether this sort of mass at infinity, C0 mass at infinity, has any relation to the other kind of nice notions of C0 ADM mass that we already have. Okay, so I have no idea about either of these. Okay. Now, okay, maybe let me just tell you a little bit about the proofs. So first, let me explain to you how to prove the distortion lemma. So this is the lemma that says, if you couple this C0 local mass with kind of a suitably evolving test function, then the distortion of this local mass will be bounded under Ricci-DeTurck flow. Okay, and so here is the idea. If we have a metric or a family of metrics evolving by Ricci-DeTurck flow with respect to the Euclidean background, then we can consider this perturbation equation. Okay, so HT is, the Ricci-DeTurck flow minus Euclidean space. And so it has this really nice perturbation equation, okay? So basically it looks like a heat equation. And then we have these terms that are quadratic in the gradient. Okay, so, now if I want to test what happens to my C0 local mass, under Ricci-DeTurck flow, well, I can just plug in this evolution and let's just see what happens. Okay, so here we are integrating this. Okay. And so now, okay, so this just comes from the definition of the C0 local mass. And so here I've just plugged in the evolution of GT minus delta, okay? And so, okay, this Q of nabla H is these two terms. I couldn't fit them on the slide. Okay. And so it turns out that thanks to the estimates of Cohen-Lamb, actually, we don't have to worry about these quadratic terms. So this is somehow like very surprising. But, you know, probably no one remembers, but we know that this Ricci-DeTurck flow of Cohen-Lamb is bounded with respect to this X norm, which means that not only does it say sort of C0 close to Euclidean space, but actually you have a little bit more control. And you have precisely the control that you need to control these terms when you integrate over, you know, over this annulus and this time scale. And so actually it turns out that the integral over this domain of these quadratic terms is going to be bounded precisely by r raised to some exponent, and it's going to be exactly the exponent that is on the right-hand side of this lemma. Okay, so this, when you integrate over this domain, these quadratic terms are going to be bounded exactly by r to the n minus 2 tau. Okay. And so, you know, thanks to the decay rate on tau, this is going to go to 0 as r goes to infinity. And, you know, the thing that kind of saves us here, like the reason that this works, is that in these quadratic terms, the h appears twice, or, you know, nabla h appears twice. Okay, and so that's why there are two here. Instead, you know, if we didn't have two of the h's, then we would get r to the n minus 2 minus tau, and that would not be good enough. And so, you know, somehow the fact that there are two h's or nabla h's in the quadratic term is very important for being able to use the estimates of Cohen-Lamb. And so we have no such luck, of course, with the delta h term. And so, you know, what I'm going to try to do then is, instead of trying to bound the delta h term directly, what I will do is now I will just hope that we have some evolution for phi that can cancel out the delta h term entirely. Okay, and so, and that's exactly what I do here. So this evolution where we take phi to evolve like the radial derivative of a backwards heat equation is precisely the evolution you need to cancel out these delta h terms. Okay, so you know, you would put the delta h onto everything else, and then you can just check that if phi evolves by the, you know, this almost backwards heat equation, then these delta h terms will exactly cancel out, and we'll just be left with the quadratic terms, which are bounded thanks to the work of Cohen-Lamb. One thing I want to mention here is that this work of Cohen-Lamb is actually extremely important, because, you know, if you just try to use kind of the derivative estimates that you would expect for the Ricci-DeTurck flow, so, you know, the derivative is bounded by you know, c over square root of t, that would actually not be good enough here, right? Because you would be integrating something like 1 over t down to 0. And so that would not be good enough. So somehow these estimates of Cohen-Lamb are really good and very helpful here. Okay, so this is basically how you prove the distortion lemma. You know, you use Cohen-Lamb to notice that actually you don't really have to worry about the quadratic terms, and then you have to use this special evolution for the test function to cancel out the Laplacians. Okay. All right. And so maybe now I will say a little bit about how you would prove this monotonicity theorem. And so this is just based on this observation of Bartnik. So, you know, Bartnik, back in his 86 paper, observed that if you have a smooth Riemannian metric, which is by Lipschitz to Euclidean space, then you have this, you know, this is true, this inequality. And so here, you know, these are just the things from the ADM mass, right? Okay. Okay, so here we are comparing kind of, I don't know, like the local version of the ADM mass at scale 10R to at scale R. And then it's going to be bounded below by the scalar curvature and then these terms. And so, okay, of course, if we're in the case where the sort of the classical case where we have C2 asymptotic flatness, then this is going to be like O of R to the minus tau. This is going to be O of R to the minus tau minus 2. this will be O of R to the minus tau minus 1 squared, right? And so these decay rates are just good enough that when you integrate over this annulus, these terms go away as R goes to infinity. And then, of course, the scalar curvature is non-negative in the smooth version of the problem I'm considering. Okay, but obviously this analysis does not apply to us for various reasons. I mean, first of all, we are interested in C0 metrics, so this part doesn't make sense, and we also don't really have a well-defined notion of scalar curvature. But actually, that's not the only problem, but the other problem is that we don't have this kind of decay on the derivatives. Okay, so somehow we would like to make this argument of Bartnik work, but it doesn't work in the C0 setting. So as I keep saying, what we're going to do is we'll run the Ricci-DeTurck flow. Okay, so we'll run the Ricci-DeTurck flow. Okay, never mind. Yeah, okay, actually, maybe I will get into the details now. So what we will do is actually first, we will take R, okay, sorry, this is G in coordinates. So we'll take R very large so that on this annulus of size approximately R, the metric is, close to the Euclidean metric like R to the minus tau. Okay, so this is possible because we're just working on an annulus of size R. And then we, restrict that metric to a slightly smaller annulus and extend it to a metric, which I'll call G0, defined on all of Rn. Okay. And so then I can find a Ricci-DeTurck flow starting from that extended metric. And then I can perform this calculation of Bartnik at the time t slice of the Ricci-DeTurck flow that corresponds to this extended metric. Okay, so now everything has t's on it. Okay, so this all is happening at time t. This is all happening at time t. Okay. And so now I'm kind of in a better position because now I have a little bit of control on the derivatives. Okay, so, I don't get that much control, but I at least have control that looks like C over root t. Okay, and so what I need to do now is I just need to make sure that I run the Ricci-DeTurck flow for long enough so that I get good enough control here so that I can carry out this calculation of Bartnik. But, I also shouldn't run the Ricci-DeTurck flow for too long because if I do that, then I won't be able to use the distortion lemma, okay? And so taking t like approximately r squared, actually a little bit before r squared, is sort of good enough to carry all of this out. Yes, okay. And so yes, as I said, I'll take t like r squared, but I'll stop a little bit before then. And I should just take this exponent to be very small depending on t so that this r raised to this power still goes to 0 as r goes to infinity. Okay. And then to show coordinate invariance, well, okay, there are a couple things I didn't mention. So to show coordinate invariance, I would basically just like to glue the transition map of the two C0 asymptotically flat coordinate charts to like a Euclidean isometry. You don't have quite enough control on the derivatives to be able to do that. And so first you have to mollify, but this kind of goes through like you would expect. And then here, I have this computation. This looks like a computation for the C0, the sort of classical local mass. I need to turn this into a statement for the sort of C0 local mass. But actually it's, if you have a smooth metric, it's fairly easy to switch between them. Okay, I think that is all I will say for now. I'm happy to answer any questions. Thanks for your attention.
Thank you very much.